Hey, what's up, guys? Okay, so welcome to my quantum complexity lecture. So I will keep going about talking about the BQP. Okay, so previous what we have shown is that right, P is a subset of BPP, and there is a subset of BQP is a subset of BP and the P space, and the XP. Okay, so the natural problem is the following, right? Is this part. So this BPP is like you can imagine that BPP is a classical computer, and the BQP is the quantum computer. Okay, so the famous, the famous, the famous, the famous conjecture or the famous uh people believe in a computer science called extended Church theoresis. Okay, so Church theoresis basically say the following. So basically, any physical computational model or any computational model that humankind can use, right? Any physical computational model is equivalent to, or it should be polynomial equivalent to BPP. Okay, so simply speaking, is that any computational word that any computational architecture you can use is BPP. Okay, uh, so but it seems like, right? But it seems like, right, BQP is powerful. I should say more powerful than BPP. Okay, but the problem is that you cannot prove this, right? But it's hard, but it's hard to prove it to show this. Because the reason is if BPP is different from BQP, then obviously the P is different from P space. Right, so this is a huge, right? This is a huge results that we don't know, right? Because we don't even know that P is different from P space. Okay, so if you prove that BPP is different from BQP, then it's you make a very huge, complexity word. Okay, but in the computer science, that one can do the so-called oracle separation. Okay, so oracle separation means that you can find oracle. Maybe you can use one oracle to separate the complexity class. Okay, so there is a famous result that why P versus NP is hard. Because there is a theorem that you can find oracle A such that P to A is the same as NP to A. And there's oracle B such that B to B is different from NP to B. Okay, so this result tells you that you cannot use the diagonalization method to prove P is different from NP or P is the same as NP, right? Because there's a oracle separation which make it the same or make it a difference. Okay, so the goal is to construct the right. So in general, if I want to prove that C1 is different from C2 in the complexity class, right, usually this is hard. But I can prove the weaker results. Right? In general, I can find a oracle O such that maybe C1 O is different from C2 O. Okay, so this is a weaker results. Okay, so our goal for this video is construct the oracle O such that the BPP O is different from BQP O. Okay, it turns out that this problem is very simple, called the Simon's problem. I think everyone knows about this in quantum computing. But there's one can use this oracle to make this Simon's problem like maybe more interesting or however. Okay. Okay, so let me just, so the problem is the following: 0, 1 to n. f is a function you want to n, and the promise to be either the first one is that f is 1 to 1, f is 1 to 1, basically, or f is injective. Okay, the second is that there is this s we don't know, such that for every x not the same as y, f of x equals f of y, if and only if x beats some s equals to y. Okay, so what I'm saying is that there's a hidden s, right? Hidden s that you can every two element, if they are the same, that means that they're correspond. Their x direct sum of s will be the bitwise sum. The bitwise sum of s will be y. Okay, or basically another ways, this is another form of the hidden subgroup problem. Okay. Okay, so this is the Simon's problem. Okay, so the goal is to find s, or basically check it's 1 or 2. Okay. So classically, so this f is our oracle. Okay, so f is our oracle. Okay, so this oracle computational model do the following. Basically, this u, x, y will be the same as, let's call this f, uf, right, will be the same as x, and y direct sum f of x. This is like a common computational model that people like to use. Okay, so our goal is to show in this Simon's problem, basically the BPP of this O is different from BQP to O. So we need to show that this Simon's problem. So on the F, right? So this Simon's problem is in BQP to O. Basically, you can quantum efficiently solve, but classically not easy to solve, right? So but Simon's problem, hopefully not in the BPP to O. Okay, then we show that this is different, right? Because I find some guy here is not in here. Okay, so let's prove 2. So right, so we need to show that this is BPP to O, right? But this is simple, right? Because you actually got 2 to N, right? So you need to find S. Okay, but the only way you can find S is to find X and Y were different. If they are different, then you can compute S by using X bitwise of Y. Okay, so basically it's just keep query F until you find X different from Y, such that f of X equals to f of Y. Then you can compute S equals X direct sum Y. Okay, so basically this is the same as the birthday paradox. If you haven't seen my video, that you can check birthday paradox. But birthday paradox basically say the following: say that if n people, or sorry, I should say, okay, if there are n birthdays that one can randomly choose his birthday. If you're a birthday, then you only need a square root of n people. Then you already have the high probability that there are two people have the same birthday. Okay, so this is, for example, right, 365 with square roots. if 23, you can show that if you are 23 people, that I mean it's not 23, but what I'm saying is that you can prove that maybe you just need a square root of n or order of square root of n people. It should be omega. Okay, you only need a square root of n people that you will have constant probability that higher than you will already have the constant probability. Okay, and this is the best. Okay. So let me just quickly give the proof. It's just a sketch. So if n people, right? So the first one can the probability that I can calculate the probability that no collision is equal 1 times the second guy, right? Second guy can have 1 minus 1 divided by n, right? Because second guy cannot choose the same birthday as first guy, and the third guy is here, and this until maybe you get, let's say you total have n people or minus 1 people. We do have n people, and the final guy is like minus 1. So imaginary is large. So this is the exponential 1 minus 1 divided by n. So the tool what we use is 1 minus x is close to exponential negative x. By the way, these are like comma analytic tool that you should, or at least it should be like familiar with you. Otherwise, that okay. So it's this like n. Okay, right? So it's n minus n squared divided by 2n. So in order to this to be constant, that our n need to choose the order of n, square root of n, right? Because for example, I want this guy to be 1, that then my n squared is to like 2n, right? So basically, it's the order of square root of n. Okay, so Simon's problem is not in BPP to O, right? Because we need we at least need like 2 to the n divided by 2, right? Because total we have 2 to the n input, and take a square root, so it's 2 to the n divided by 2. Sorry, 2 to the power of n divided by 2. So it's not in BPP to O. Okay, so quantum, right? Quantum computing, right? So famous, so amazing. Okay, so you have this circuit. Okay, so you have this circuit, and your initial state size just basically 1 divided by n choose 2 x 0 1 to n. So if this is here, right, after you apply hard mod, so this is x 0 1 to n. Once you apply uf, then you will get this. So let's say this is stage 1, stage 2, and the stage 3. Okay, so stage 1, stage 2, you get x. So I'm very sloppy, so I write this. And I know this, right? I know this is basically the I can write this as this, right? Because I know that f of x is the same as f of y. So I can write this. Okay. Oh, so it's very bad. Let me just do this. Okay, so let's see. So I think this algorithm looks a little bit weird. So after apply, this is a second step. And okay, so I can write this as this. I can write this to be let's say I can write this to be what? If I fix this to be y, right, there will be y plus y direct sum s, right? I can write as this, and then sum over y, right? But in this case, that I create another number, right? So I should take to be there should be another square root of 2. Okay, so this is the second step. Now I can apply the Hardeman again. Okay, so third step is here. I apply the Hardeman again, and I will get the. Okay, so this is just the calculation. Let me just quickly go through. So if you can apply Hardeman again, then you get the following. You get the x y plus minus 1 x direct sum y s. Oh, it's very bad. What the hell is going on? Okay, so yeah, I apply this. Then I need to yeah here, and yeah, so it should be x, yeah. Yeah, I apply a Hadma on the yeah, I applied the Hadma on the first. Oh, yeah. Okay. So I understand what is. Sorry, I'm stupid. Okay, so after this second, right, we first measure the third qubit. We first measure this qubit. Right, it's the same. So we measure this qubit. Okay, so after we measure this qubit, right, we will fix y. We will fix y, right? So after we measure the second qubit, right, then our phi will be square root x plus s. Okay, and yeah, so this is this right here, and then that we apply Hardeman. Okay, so this is the. Okay, so we start from here and apply Hardeman. Okay, so we get the 1 over square root of 2 and plus 1 summation y minus 1xy minus 1x plus sy. Okay, so let me just recall that the Hardeman icon x will be if you add 2 to the n of lambda, right? It's basically is minus 1 to the x y. If you're like very like mathematic, you can say yeah, it's the character, the group representation of z2 to the n. It's fine. Okay. So it's here. This times y. Okay, so you can represent as this minus y x y 1 minus 1 plus minus 1 x s y x y and s y. Sorry, this is s y. Right, because I pull out minus 1 to the x y, so it's 1 plus minus 1 to the y s. Okay, so now I measure y. Okay, so you will get y, right? But the y you get must be y dot s is 0, right? Because if y dot s is 1, then you will get 0. Okay, so you measure y. Okay, so any y you measure must satisfy y dot s is 0. Okay, so basically, simple speaking, is that yi sum I sy I from 1 to n is 0. Okay, so you can just make O and queries. Okay, then you will get with high probability that you will get the y1s0, y2s0, y3s0, yn s0 that you can solve in the linear equation, right? So you solve this equation in F2 and n by equation in F2 to n to find a non-zero s. Okay, so it's linear equation, and then you just need O and Q rays. Okay, so this is why. So we proved that the Simon's problem is indeed a BQP to O, but it's different from a PPP to O. Okay, so this is our results. Okay, and the recent there's a recent progress, or is very famous, that one can show that there is oracle A such that the entire polynomial hierarchy A is different from a BQP to A, and this is called a Fourier relation. Okay, it's very interesting that I will make a video on it, definitely. Okay, see you guys next video.